You know what's weird? Right now, you're watching this video on a device that's processing millions of electrical signals every single second. And here's the crazy part. Every single one of those signals boils down to just two options, 0 or 1, off or on. That's it. Your phone can run Spotify, stream Netflix, and order you Starbucks all at the same time. But underneath all that complexity, it's just billions of tiny switches flipping on and off. Sounds pretty simple, right? But here's the question nobody really asks. Why? Why do the most sophisticated machines humans have ever built use the simplest possible language? I mean, we have 10 fingers, we count in tens. Our entire number system is built around 10 digits. So why don't computers use 10 states instead of just 2? Everyone says it's because binary is simpler or more efficient. And sure, that's part of it. But here's what nobody tells you: there's a much deeper reason, a physical reason. And it has everything to do with what's actually happening inside your computer right now. In the next 15 minutes, you're going to understand why every computer ever built speaks in binary. And it's not just about math or programming. It's about the fundamental physics of how matter behaves when you make it really, really small. Think about the device you're holding right now. Could be your phone, could be your laptop. Maybe you're watching on your TV. Whatever it is, there's something wild happening inside it that most people never think about. There are billions of tiny components in there, like actually billions. Your iPhone has something like 15 billion transistors packed into a chip smaller than your thumbnail. That's more transistors than there are people on Earth, all crammed into a space you could lose in your couch cushions. And every single one of those transistors is making a decision. On or off, 0 or 1, high voltage or low voltage. That's the choice. That's the only choice they ever make. But here's what's really happening that nobody talks about. These aren't just abstract mathematical concepts. 0 and 1 aren't just symbols programmers chose because they liked how it looked. They're representing actual physical states, real voltages, real electrons moving through real silicon. When your computer stores a 1, there's actually more electrical charge sitting there. When it stores a 0, there's less. It's as real as water in a glass. You can measure it with instruments. You can see it on an oscilloscope. And this matters because of something most people don't realize about electricity. It's messy, like really messy. Picture this. You're trying to have a conversation with your friend across a crowded Starbucks. People are ordering complicated drinks. The espresso machine is hissing. Someone's baby is crying. Music is playing. It's chaos. Now imagine trying to communicate something precise in that environment. Not just, hey, what's up, but exact information, like the digits of your credit card number. Every single digit has to be perfect. One mistake, and the whole thing fails. That's basically what's happening inside your computer. Except instead of background noise from coffee shop chaos, you've got electrical noise. Random fluctuations in voltage, heat causing electrons to jiggle around unpredictably. Electromagnetic interference from all the other signals zipping around nearby. Your computer's trying to send precise information through this electrical chaos billions of times per second, and it can't afford to make mistakes, not even tiny ones. So here's the choice engineers faced when they started building computers. They could try to use many different voltage levels, like 10 levels for 10 digits, just like our normal number system. That would be analog thinking. Or they could use just 2 levels spaced really far apart. That's digital. And here's where the physics gets interesting, because this isn't just a preference. It's a fundamental constraint based on how the universe actually works. Let me paint you a picture of what goes wrong with analog. Imagine you're trying to represent the number 7 using voltage. You decide that 0 volts means 0 and 5 volts means 9. So 7 would be somewhere around 3.5 volts, right? Sounds reasonable. But now you've got a problem, because when you measure that signal, you might read 3.4 volts or 3.6 volts. And you need to figure out, is that supposed to be a 7? Or is it a 6 that got a little noisy? Or an 8 that lost some charge? You're basically playing a guessing game. And when you're copying this signal millions of times, when you're sending it through miles of microscopic wires, when heat and interference are constantly messing with it, those small errors add up fast. It's like playing telephone at a Super Bowl party. The first person whispers, "Meet me at Target at 3." By the time it gets to the 10th person, it's become, "Eat meat and forget at tree." The message degrades with every copy. But binary is different. Binary doesn't play that game. Instead of 10 voltage levels squeezed close together, you've got just 2. And here's the brilliant part. You space them way apart. Like as far apart as physics allows. Let's say 0 volts is a 0 and 5 volts is a 1. Now, when you read the signal, you don't need perfect precision. You just ask one question. Is this voltage closer to 0 or closer to 5? If you measure 2 volts, that's clearly a 1. If you measure 4 volts, still a 1. Heck, even if you measure 1 volt, you can figure out what it's supposed to be. Because there's this huge gap in the middle, this massive buffer zone where noise can happen and you still know exactly what the signal means. It's like the difference between trying to identify a specific shade of blue versus just figuring out if something is blue or red. One requires precision. The other, you can tell from across the room. And this is what makes digital systems so absurdly reliable. Every time the signal gets copied, every time it travels through another wire, every time it gets processed, it gets cleaned up, restored to either 0 or 5 volts, the noise gets erased. Think about photocopying a document at your local library. You make a copy, then you make a copy of the copy, then a copy of that. After 20 generations, the image is getting pretty degraded, right? Lots of spots and smudges and blurriness. That's analog. Every copy is slightly worse than the original. But imagine if every time you made a copy, the machine looked at each letter and asked, is this supposed to be an A or a B? And then printed a perfect new version of whichever letter it detected. You could make 1,000,000 copies and the millionth would look identical to the first. That's digital. That's binary. That's why your computer can process the same piece of data billions of times without it turning into garbage. Now here's where we need to talk about what's actually doing this processing. Because binary isn't just some abstract concept floating in the ether. It's embodied in physical objects, real devices made of real materials. And those devices are called transistors. A transistor is basically a switch. That's it. That's the whole thing. It's a tiny electronic component that can be either on or off, conducting electricity or blocking it, 1 or 0. But here's what makes transistors absolutely magical. They're not mechanical switches like a light switch in your house. There are no moving parts. Nothing physical flips or clicks. Instead, they use the quantum properties of silicon to control the flow of electrons. Silicon is this weird material that's not quite a conductor like copper and not quite an insulator like rubber. It's a semiconductor, which means under normal conditions it doesn't conduct electricity very well. But if you do certain things to it, like apply a voltage in the right place, you can suddenly make it conduct or stop conducting. It's like having a door that's normally locked, but when you hold up the right key nearby, even without touching the lock, the door swings open. That's basically how a transistor works. You've got 3 terminals: source, drain, and gate. Normally, electricity can't flow from source to drain. The path is blocked. But when you apply voltage to the gate, you create an electric field that changes the properties of the silicon underneath. Suddenly, electrons can flow through, the switch is on, you've got a 1, remove that gate voltage, and the path closes again, the switch is off, you've got a 0. And this happens fast, like stupidly fast. Modern transistors can switch on and off billions of times per second. That's faster than you can blink, faster than sound travels, faster than most anything in your daily experience. But here's the thing that connects back to why we use binary. Transistors aren't great at half measures. They're not designed to be kind of on or mostly off. They're designed to be completely one thing or completely the other. This isn't a limitation, it's intentional. Because when you're making something incredibly small, and we're talking about transistors that are just a few dozen atoms wide, you need clear, unambiguous states. At that scale, quantum effects start to matter. Electrons don't behave like tiny balls rolling down a wire. They behave like waves, like probability clouds. Weird stuff happens. If you tried to make a transistor that could exist in 10 different states, you'd be fighting against the fundamental physics of how electrons behave at tiny scales. The states would blur together, quantum tunneling would cause electrons to jump where they're not supposed to be, heat would cause random fluctuations that you couldn't control. But two states? Two well-separated states? That works. That's stable. You can make it robust enough that quantum weirdness doesn't mess up your data. It's like trying to balance a pencil on its point versus laying it flat on a table. The balanced pencil has infinite possible positions as it falls. The flat pencil has basically one stable position. Which one is more reliable? Binary gives you that stability at the atomic scale. Now let me tell you something that might blow your mind. The chip in your phone right now has transistors that are about 5 nanometers wide. A nanometer is 1/1000th of a meter. For context, a strand of human hair is about 80,000 nanometers wide. These transistors are so small that you could fit about 20,000 of them across the width of a single human hair. They're approaching the size of individual molecules. And at that scale, the fact that they work at all is kind of miraculous. But the fact that they work reliably, billions of times per second, for years without making mistakes, that's only possible because of binary. Because here's what nobody talks about when they marvel at Moore's law, the observation that the number of transistors on a chip doubles about every 2 years. Everyone focuses on the, wow, we fit more stuff on the chip part. But the reason we could keep shrinking transistors for decades wasn't just about better manufacturing. It was about the fundamental robustness of the two-state system. Every time engineers made transistors smaller, the challenges got harder. Less charge to work with, more noise relative to signal, more quantum effects, more heat in less space. But because they only needed to distinguish between two states, not 10, not 100, just 2, they could keep going, they could keep making the voltage difference between 0 and 1 smaller, keep making the physical structures tinier, keep pushing the limits. If computers had been built on 10-state systems from the beginning, we probably would have hit a wall decades ago. The physics would have stopped us. There wouldn't have been enough margin for error as things got smaller. Binary bought us room, physical room, error margin, robustness. Let me tell you about 2 engineers I'll call Maya and James. Both brilliant, both working on computer systems, but with totally different approaches. Maya is working on an analog computing project. Her system uses continuous voltage levels to represent numbers. It's theoretically more efficient. In some ways, you can represent larger numbers with fewer components. She's excited about the potential, but Maya keeps running into problems. Her system works great in the lab under perfect conditions, but when temperature changes even slightly, the voltages drift. When she tries to speed up the processing, noise becomes a bigger issue. When she tries to shrink the components, the precision falls apart. She spends months trying to build better error correction, trying to stabilize the voltages, trying to compensate for all the physical factors that keep messing with her analog signals. And it works, kind of, but it's complicated, and fragile, and expensive. Then there's James. James is working with standard binary digital systems. His components are simpler in concept, just on or off. But here's what James notices. When temperature changes, his system barely cares. As long as the voltage stays somewhere in the right half of the range, it reads correctly. When he speeds up processing, the noise increases, sure. But there's enough margin that it doesn't matter. When he shrinks components, they keep working because he's only asking them to do one simple thing, be clearly on or clearly off. James doesn't need complex error correction for every operation. The binary system error corrects itself automatically just by being read. Every time a transistor passes a signal to the next transistor, it's essentially asking on or off, and outputting a clean version of whichever one it detected. His system isn't fighting against physics, it's working with physics, using the natural tendency of systems to exist in distinct, stable states, rather than forcing them to maintain precise intermediate values. And here's what happened. Maya's analog system remained a research project. Interesting. Potentially useful for very specific applications, but not practical for general computing. James's binary system became your laptop, your phone, your smartwatch. Every digital device you own Notice how that worked? It wasn't about who was smarter or who worked harder. It was about whose approach aligned with physical reality at small scales. Here's what most people don't realize when they think about computers. They imagine the binary part is about the math, about how programmers write code or how data gets structured, but it's not actually about that at all. It's about physics, about the behavior of electrons in silicon, about signal-to-noise ratios, about quantum effects at nanometer scales. The math adapted to fit the physics, not the other way around. Binary code, all those zeros and ones you see in movies when they want to show hacking, isn't some arbitrary language that programmers invented and then figured out how to implement in hardware. It's the natural language of physical switches, of transistors, of anything that has two stable states. You see this pattern everywhere in nature, actually. Systems tend toward discrete states when they get small. Electrons and atoms exist in specific energy levels, not anywhere in between. Quantum particles have spin up or spin down, not somewhere in the middle. Biology uses 4 DNA bases, not infinite gradations. The universe seems to prefer distinct states over continuous ones at fundamental levels. Binary computing isn't fighting that, it's embracing it. And once you see it this way, everything changes. Computers aren't these magical thinking machines that happen to use binary for efficiency. They're physical systems built from billions of tiny switches that can only reliably exist in 2 states because of the laws of physics. The computational power doesn't come from the individual switches being smart. It comes from having so many of them that you can combine those simple on-off signals into complex patterns, patterns that can represent anything. Numbers, letters, images, videos, the entire internet. It's like pointillism in art. Each individual dot is simple, just a spot of color, but combine millions of them in the right pattern and you get a masterpiece. Binary is the dot, the pattern is everything. So here's what we've uncovered. The reason computers use binary isn't really about math or efficiency or programmer preference. It's about the fundamental physics of making reliable switches at microscopic scales. Transistors work best as binary devices because they're fighting against noise, heat, quantum effects, and all the chaos that happens when you shrink electronics down to just a few nanometers. 2 well-separated states gives them room to breathe, room for error, room to stay reliable even when conditions aren't perfect. And that reliability is what made everything else possible. Made it possible to shrink transistors to molecular scales. Made it possible to pack billions of them onto a single chip. Made it possible for your phone to process more calculations per second than all the computers that helped land humans on the moon. The question isn't whether we could build computers differently. We probably could, for specific purposes. Analog computers exist. Quantum computers are exploring different paradigms entirely. But for the general purpose digital revolution that transformed human civilization, for the devices that connect billions of people and process quintillions of operations per day, binary was the only path that worked, because it's the only path that aligns with how matter behaves when you make it really, really small. You're not just using a tool that speaks in zeros and ones. You're using a tool that's whispering in the native language of physics itself. So next time you're scrolling through Instagram or playing a game or video calling your friend across the country, remember what's actually happening. Billions of tiny switches, each one making the simplest possible choice billions of times per second. On or off. Yes or no. 1 or 0. And somehow, from that simple foundation, you get everything. Every app, every video, every connection, all of human knowledge in your pocket. Because the universe, it turns out, speaks binary too.